In this section, we're going to study particularly slope fields with a little bit of an introduction about just general differential equations. The second part of the title here that says Euler's method, we are actually not going to cover. Euler's method is not on the AP exam. For AB students, it is a BC topic only. So this is definitely not something that we need to worry about here. All right. So there are two main objectives here. The first is to use an initial condition to find a particular solution. And that phrase particular solution is something that we will spend a lot of time talking about. To a what's called a differential equation. I think we have used this term in the past, but I'm going to define it again here in a moment. And then we're going to use slope fields to approximate the solution of a differential equation. And these approximations, it's important to understand that our focus here is on graphing solutions. We're not actually going to have a solution that is an algebraic function or formula. We are going to be graphing. All right, so what exactly is a differential equation? In this text, we learned that physical phenomenon, a lot of things that happen in the real world, can be described with differential equations. A differential equation is essentially any equation that has a derivative in it. All right? So a differential equation, by definition, is simply an equation containing a derivative. Generally, we usually deal with our differential equations that have multiple variables. So they'll have the derivative, as you see here, y prime, but they might also have other variables like the independent variable x and the dependent variable y. And y, if we knew what y was, y would be considered the solution to the entire equation. So in other words, if you plugged in the function y, if we knew what the function y was and we plugged it in here for that y, and then we also took y's derivative and we plugged it in here, and then we multiplied it by 2x, obviously subtracting 3 times the original y function, all of that collectively should equal 0. So the solution to a differential equation is the function y that solves the differential equation. All right? And in order to solve, of course, you have to also have the derivative of y. But if you have y, you should be able to take its derivative. All right? In section 6.2, we're going to look at some of the applications of the differential equation concept. And then in 6.3, we're going to spend a lot of time, and that's our last section for this unit. We're going to spend a lot of time talking about how to find a solution. In particular, how to find using a method called separation of variables. And that will conclude the unit and probably the course for this year. All right, a function y equals f of x, as I said, is the solution. So if you knew what y was, it would solve the DE. This is an example. There are infinite possible differential equations. Just come up with anything that involves a derivative and some other variables, and you've got a differential equation. All right. It is a solution if the equation is satisfied when y and its derivative are plugged in, essentially. And so they give you an example here. It says, for example, differentiation and substitution would show that if this was y, e to the negative 2x, if this was some function y, then it would solve this equation. The derivative here, if you took its derivative and you plugged it in there, and then you added to that 2 times the original, you would get 0. And I think you could probably see that pretty quickly here. If I take this function, this e to the negative 2x function, and I calculate its derivative, y prime would be e to the negative 2x times the derivative of the exponent, which is another negative 2. All right, so that is negative 2 e to the negative 2x. So if I take negative 2 e to the negative 2x and I put it here, because that's the derivative, right? And then I take the original e to the positive e to the negative 2x and I put it here, then I've got the negative 2 e to the negative 2x plus positive 2 e to the negative 2x. And of course, when I add them together, I get 0. So this solves this original y solves this equation. That may not be, however, the only solution. It can be shown that every solution of this differential equation is going to hold the form any constant c times e to the negative 2x. In this particular solution, the c value was 1, but it really could be any constant, and this would solve this differential equation. All right? And so if it's any constant, then that's what we call the general solution. So if there is a constant, it's a general solution. If the constant is, if there's a constant c, if there's a variable c unsolved for. But if we know what that constant in front is, then that, in this case, it's 1 right here, then that is the particular solution. All right, so difference in terminology, differential equation, any equation involving a derivative. The solution is some function f of x that makes the equation true. But you can have a general solution, which includes an unknown constant, and then you can include or you could have a particular solution for which that constant is solved for. All right, let's go into an example. Here we are asked to determine whether the given function, and there are 3 different functions given, so 3 problems, is a solution to this differential equation. Notice these 3 functions are very different from each other. Well, these 2 are pretty similar, but this one's very different. So to prove that it's a solution basically means to take the y and plug it in where appropriate. So I need y double prime. If this is y, I need y double prime to put in here, and then I can put my y in for y. So let's start by finding y double prime for a. All right. Y equals, y prime equals cosine x, and then y double prime would be negative sine x. All right, so if that's my y double prime, then this equation becomes negative sine x minus, remember my original equation is y double prime minus y equals 0. All right, that's my differential equation here. So negative sine x minus the original sine x minus y, minus sine x equals 0. And of course that gives me negative 2 sine x equals 0, which is not true, right? And so since it's not true, wrong color here, sorry. Since it's not true, this is not a solution. So A fails. It is not a solution of the differential equation. Let's move on and try B. In B, again, I have my y. It's equal to this function, this exponential function. I need y double prime in order to plug into that differential equation, so I'm going to have to find y double prime. So y prime equals 4e to the negative x times negative 1, which of course is negative 4e to the negative x. And then y double prime, that negative is just going to end up being multiplied again, so it becomes positive 4e to the negative x. All right? If I plug that in, 4e to the negative x minus 4e to the negative x is, of course, 0. And so, yes, it is a solution. All right? Let me use this color here. C. Now this one is general because they've left the constant in front as c. So y prime is a constant times e to the x, and then y double prime is going to be, again, a constant times e to the x, so it doesn't change. And so this one's pretty obvious, right? If you put c e to the x in here, and then the original c e to the x, which is the same thing, in here, you're going to get 0 equals 0, right? C times e to the x minus c times e to the x is definitely 0. So yes, this one is also a solution. All right? So to solve a differential equation, or to verify, I should say, that a function is a solution to a differential equation means to basically just plug it in however appropriate. Some differential equations you don't have a second derivative. You have, like the example we had above, you only have a first derivative here. Some of them, of course, you do have a second derivative and you got to keep going. All right, let's move on. Now we're going to talk about graphing solutions. And this is where we're going to get into the main topic of the lesson, which is slope, or what we call direction fields. All right. Actually, I just realized that I think that title is on the next page, but that's all right. Geometrically, all right, so we're going to a graph. Geometrically means we're on a graph. The solution of a first order differential equation, and first order means y prime, represents the family of curves, all possible curves, known as a solution curve, right? That's general solution. One for each value, so there's one curve for each value that is assigned to the arbitrary constant. So if I take this equation, which we dealt with a little earlier, and I just change the c value, then the general solution would be the collection of all curves with the defined c value. And so there's an example of it here. If I let c be 1, I get this curve. If I let c be 2, I get this curve. If I let c be -1, I get that curve. If I let c be -2, I get this curve. And of course, there are infinite possibilities for what you could let c be. And no matter what value is plugged in for c, you get the same, the value, no matter what value is plugged in for c, the equation will still solve this differential equation. All right, this function y still solves it. So most of our work is in finding either a graph of a solution, and usually a particular solution, not all family members, because you can't actually express all family members. So we're looking for graphs, or we're looking for the actual function y equals, or f of x. And we have to calculate that function somehow when only given the initial differential equation. All right? Again, calculating the function f of x is something we're going to do in section 3, 6.3. Example 2. Find a particular solution. So they want us to find the solution to this differential equation. It says, for the differential equation, verify that cx cubed is a solution. Of course, assume x is positive. That's important for this problem. Then find the particular solution determined, so there's two parts here. Then find the particular solution determined by the condition where y equals 2 and x equals 3. So let's start out with verifying. If I believe that y equals cx cubed is a solution, then notice that the differential equation requires y prime. So I'm going to start out by finding y prime. And y prime would be c times the x cubed. Remember, c is just a constant, so it's just hanging out. But the derivative of the x cubed, this is a power rule, power function here, 3x squared. So I can rewrite this as 3 times whatever c is times x squared. All right? So if I plug that back into my differential equation here, all right, then I get x times that y prime is 3cx squared, and then minus the original, minus 3 times my original function y, so cx cubed, and that is all supposed to equal 0. Well, of course, if you look at it, that is clearly true. 3c, let's make that c capitalized, cx cubed minus 3cx cubed is, of course, equal to 0. So it checks out. All right. Then they go on and they say find the particular solution for the case where y is 2 and x is 3. So in my differential equation, in my function y, if I let x be 3 while y is 2, then I get 2 is equal to c times 3 cubed, which gives me 2 over 27 for the c value. And therefore, my particular solution is y equals 2 over 27 x cubed. All right. In the case where when x is 3, y is 2, this is the function. And if you took the derivative of this function and then took the original function again, and you plugged them both in here and here, it would solve this equation I've got boxed in red. All right. Then off to the right, we've got a graph of this particular situation. The solution looks like this. All right. And they said x must be positive, so they've got an open dot here at the origin, and it's increasing off to infinity. Notice that it has to go through the point 32 because that is on the curve. All right. It says note that to determine a particular solution, the number of initial conditions must match the number of constants in the general solution. The number of initial conditions has to match the number of constants. So if I have one constant, I have to have initial conditions for the variables for that constant. All right. Let's move on. Okay, so here's the official start of our direction field. So I'm going to say this is page 3 of the notes. The next page as well, I highly recommend that you print these out, actually, because you don't want to have to resketch all of this. All right, I have posted these notes. Oh, my screen just locked. I have posted these notes. Let's see if this works. To the portal in blank copy. I've posted these notes to the portal as a blank copy, and I highly recommend that you print page 3 and 4 out so you don't have to draw these graphs and things. It's going to make the work go much simpler, and you definitely need practice on this stuff. All right, so again, slope field, direction field. Suppose we are asked to sketch the graph of a solution to an initial value problem. All right, sketch the graph of the solution. We're not finding the solution, which would mean we're finding y. All right, we are sketching it. In this problem, our differential equation that's given, and please understand, a lot of students get caught up in these differential equations, and they start to think that the equation I boxed is like always the same equation. But the differential equation changes for every problem. This problem, we've got the equation is y prime equals x plus y. The previous problem, we had x times y prime minus 3y equals 0, right? The equation could change. Y double prime minus y equals 0. Every problem, you're going to have a new differential equation. All right. So here, we do have an initial condition, 0, 1, but we're not going to use that until we get to the point where we can graph. All right. Here's how we sketch the slope field. We choose values for x and y, meaning we select points off of the graph, off of the grid, the xy coordinate system. And then we use those points to calculate y prime. So I've got a 3-column table here going on. Again, y prime, as we know, is the slope of the curve, right? If y prime represents the slope, then what we're going to do is we're going to create something that looks like this. We're going to create a slope field. All right? So let me begin by saying very simple values. Let's say x is 0 and y is 0. Well, of course, in my function, if x is 0 and y is 0 in my differential equation, then I get 0. Okay, well, how does that translate on a graph? That is a slope of 0. So I'm just going to put a little line here at 0, 0 on the graph, a little mini slope, a line with a slope of 0. All right? So then if I choose, let's go -1, -1. Well, if both x and y are -1, then the equation says I add them and I get -2. So I come over to the graph, and at -1, -1, at the point -1, -1, I'm going to graph a line that has a slope of about -2. That's probably a little bit too shallow. I got to go down 2 over 1. I think that's still too much. Let's say it's like that. There we go. Slope. Now, how do I know where it is? I don't, honestly. If you really do want to know, you could grab a ruler, or in this case, that's about right, actually. I just drew a line with a slope of down 2 over 1. All right, down 2 over 1. You could grab a ruler and lay it out on the grid if you were worried about whether or not it was correct. They don't allow rulers in the AP exam, but you're going to be taking it by home this year. So, all right, let's keep going. So if I want another point, I would say let's go -1, +1, right above it. So that's this point right here. And of course, if I do that, I get a slope of 0 when you add them. And so on the slope field, my line is just a little, again, another little horizontal line. Let's go below at -1. Oh, I see what I did. I put that point in the wrong spot. This point right here, I'm sorry. This one right here, we're supposed to be at -1, -1, not -1, 0. Or, yeah, -1, 0. It should have been here. That's where that slope was supposed to be. All right, sorry about that. If I use -1, 0, then I get a slope of -1, and that line should be a little more shallow, about half as steep, right? So something like that. There we go. And I could continue this until I have an entire table filled. You can see that this is an extremely tedious process, right? Ultimately, when I'm done, I would end up with a graph that is filled out with these little mini slopes and looks like this. All right? Now, you're probably going, holy crap, how many of these things do I have to draw? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 121 different little slopes that are drawn here. And of course, they're going, if you notice, they went, it looks like every half a value. So 0, 1/2, 1, 1.5, 2, 2.5. 121 little mini slopes. If I was filling this whole thing out, I would have at least, this looks like it goes 4 by 4, I would have at least 16 different little mini slopes here. You would never be asked to do that many on an AP exam or something, ever. The most that I've ever seen asked for is 9, to be honest with you. All right, so 9 little mini slopes. We've done 4. Let's use that particular solution here. So then they gave us y of 0 equals 1. So at the particular point where when x is 0, y is 1, that means we are, I really don't have values on the y-axis, but let's say this is 1, 2, 3. So that means 0, 1 is this point right here, all right? Right here where my cursor is. If that's the case, then the solution curve, remember, all of these slopes are calculated from this equation for slope, y prime equals equation for slope. All of these slopes are calculated by that, but the curve y that solves this equation, this differential equation, would be the curve that goes through these lines. And in our particular problem, we want it to go through the point 0, 1. So we draw the initial condition point, 0, 1, and then we use that point to draw a curve, and we just kind of guide the way we draw the curve is guided by the little mini slopes. So I'll start at the point, and then I'll go off to the right. It tells me to shoot in this way, and then I'm coming up here, I'd say like that. Kind of is guided by the slopes to make a curve that looks something like that. All right? And then I can go draw the left side. It's flat right there at 0, 1. So it's shooting me, no, it's not quite flat. It's angled down just a hair. So it's shooting me still down a little bit, but then this point over here tells me to flatten out. And then it's starting to push me. It's pushing me, it looks like this way. All right, now, is it perfect? No, absolutely not. Somebody else might draw theirs slightly higher or slightly lower, but it's pretty close. This curve, if I knew what that function was, this is the solution to y prime equals x plus y at the particular point 0, 1. All right? Obviously, you could draw infinite solutions on this graph. Maybe not infinite, but you could draw plenty of solutions on this graph. For instance, if I said, oh, let's go 1, negative 2. At 1, negative 2, starting right here. If I start at that point, the solution curve at 1, negative 2, then it pushes me horizontal and then starts to clearly bend upward. All right? And then if I go off to the right, I'm horizontal, and clearly these values are making me flatten out in this way. I would note, see how these lines are all dashed like that? It almost looks like there's a horizontal asymptote, or sorry, a slant asymptote on this curve. All right? But this curve in red is a particular solution to this differential equation. It just happens to be that our initial condition was 1, negative 2, so the curve is positioned in a different spot. But all curves that can be drawn here are part of the same family. All right? All right, again, the red curve was just an extra example. It was not part of this problem. It did not ask you to draw this. The purple curve here was the only one they were asked to draw because they gave us 0, 1. So you create a table, you calculate your little mini slopes, you draw those mini slopes, and then if you're given an initial condition, you draw a solution curve through those values. All right, let's move on. Example 3 says sketch a slope field for the differential equation y prime, so there's our new DE, y prime equals x minus y. The last problem was x plus y, this one is x minus y. And then they give us the particular points that we're supposed to use, which are negative 1, 1, 0, 1, and 1, 1. All right, so if you wanted to, you could draw a table real quick. And you'd say, okay, well, x, y, and y prime, we've got negative 1, 1, 0, 1, and 1, 1. Only one of those three values. And if you calculate those three, since y prime equals x minus y, then negative 1 minus 1 is negative 2, 0 minus 1 is negative 1, and 1 minus 1 is 0. And then you can see, when you go to put those values on the graph, at negative 1, 1, we've got a slope of negative 2. At 0, 1, we've got a slope of negative 1. And at 1, 1, we've got a slope of 0. All right, just another quick example. Number 4, if you printed out the notes, the blank notes from the portal, like I said, for pages 3 and 4, your blank notes did not have this on it, I don't believe. I forgot when I created this document to include the 3 equations, differential equations that match these graphs. All right, so identifying slope fields for differential equations. This one we are given 3 slope fields and we are given 3 differential equations. Our job is to figure out which differential equation matches the slope field. All right, the first thing I want to point out is that equations 2 and 3 here are what we call autonomous differential equations. Autonomous. And what that means is that the slope y prime is dependent on only one variable. In other words, the first one, if you look at this equation 1, y prime is dependent on both x and y. But in equation 2, the slope is dependent only on x. In equation 3, the slope y prime is dependent only on y. Why is that important? Well, an autonomous differential equation has slopes that in a line are identical. So for instance, if I look at B here, actually let's just look at A, I'm sorry. If I look at A, it looks like all of the values along x equals negative 2 have the same slope. and all of the values at x equal looks like -1.5, and all the values at x equal -1. In a vertical line, all of the values, all of the slope values are identical. And they are all dependent upon, it looks like, the horizontal position, the x position. The y position makes no difference because the slope at that particular x is the same. The slope at this x is the same. This x is the same, which means the slope is dependent only on the x value. If that's the case, then it has to be equation 2 that matches this one. All right. In B, it looks like, and again, if you didn't see that, if you didn't notice that, then what you could do is you could just start plugging in some values for x and y here and here, and then test and see which of the graphs seems to match. All right. So in B, let's say if I choose 0, 0, well, all of them are going to give me 0, so that's not the best value. Let's choose 1, 0. At 1, 0, I get a slope of 1. Okay, well, that's great, but it matches these two. Well, I already identified that one, so it's got to be this one for equation 1. But let's just try another one. Let's say this slope right here at 1, 1. All right, this slope here, 1, 1. It looks like if I was to plug 1 and 1 in here and here, I would get 2, and this little slope is 2. So I've confirmed that this has to match equation 1. All right, which obviously leaves this one to be equation 3. But truth is, we could have figured that out if we looked at this one initially. Notice that in a horizontal line, all of the slopes are identical across a horizontal, which means the y value is determining the slopes. And here, the slope is dependent on y only, so it has to be this one. All right. One other thing I'm going to point out going forward, we are going to solve in section 3. So this is a little bit of a quick preview of what's to come. We're going to solve differential equations. We're going to actually try to find the y that solves these functions. So the question might be, for instance, on equation 2, what does the solution look like? All right, what is the function y for which the derivative is equal to x? Well, you could probably come up with that on your own if you think about it carefully enough, right? What is the function y, right? Y equals what? What is the function y for which the derivative of y is just x? All right. Our job in the next section will be to take differential equations like what you see in any one of these problems. First of all, we'd rewrite, instead of y prime, we'd rewrite it dy dx. So dy dx equals x. Then, if we throw the dx to the other side, multiply by dx, we get dy equals x dx. Right? Now, if I integrate both sides, then the integral of 1 dy on the left, the integral over here on the left side is just y plus c, but I'm going to leave it off. The integral on the right side, raise the power 1, divide by the new power, is 1/2 x squared. And then if there's a c on the left and a c on the right, then combined, I could put them on one side and just call it plus c. And of course, the derivative of 1/2 x squared plus some constant is simply x, right? That is a preview of what's to come in section 3, where we use what we call separation of variables. I separated the dx and pulled it over. Separation of variables to solve. Here's the equation that makes, or here's the function y that makes this equation true. All right, moving on real quick. Example 1, and this is really the last example that we're going to work. I already put the table in here. It says sketch the direction field for the differential equation. And that is an ominous task. Just sketch the direction field because they gave us no restrictions on how many points to actually create. We could go on and find 121 points again. All right, I'm not going to do that. I'm just going to do a couple of them. So play along with me here. So let's see. If I said, let's go with points 0, 0, 1, 0, 0, 1, 1, 1. I'm just choosing points. 2, 1, and I could keep going on and on and on and on and on. Then if I'm using these values to plug into my function, let's just do this in our head. 0 and 0 plugged in here is going to leave me with -1. 1, 0 is going to give me 0. 0, 1 is going to give me 0. 1, 1 would give me 1. 1 squared plus 1 squared, that's 2, minus 1 is 1. And then 2, 1 would be 4 minus 1, or plus 1 minus 1, so 5 minus 1 is 4. All right? And I could keep doing this all day and getting as many points as I wanted. If I come over and I draw those points on my XY graph, then at 0, 0, I have a slope of -1. At 1, 0, I have a slope of 0. At 0, 1, I have a slope of 0. At 1, 1, I have a slope of 1. At 2, 1, I have a slope of 4. So that's pretty steep, actually. Slope of 4. All right, and that's as far as I went. So there we go. Again, we could keep going. We could fill this thing up. Part B says, using part A, sketch the solution curve that passes through the origin. Okay, so I would need a lot more points because I need to know how it behaves. Clearly it's going up in this direction, and then it's being shot down and it's going to do something over here. I don't have any points in quadrant 1 or quadrant 4 over here or over here in quadrant 2. I would need a lot more points to see how this thing behaves if it has to go through that origin. All right, thankfully, again, you're never going to be asked to draw 100 points or even 20 points or even 12 points in most cases. You're just going to be asked to draw like 9 points at most or something like that. So I have the direction fields printed on page 5. So here we go. All right. Notice that these points here, 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 and which other ones do we have? And, oh, you know what? I'm sorry. We did not have those two. We had that one, and then we did this one. So these 4, 1, 2, actually, that one there. I'm off, sorry. These points, my graph here goes by halves, and ours did not above. We didn't go by halves up here. These 5 points are the ones that we had. There we go. If you compare, these 5 points are the same as these 5 points. All right? But this slope field goes by half values, and it's giving us a lot more. All right? But the solution is shown over here to the right. This is the solution curve that goes through the origin. But just for practice, I highly recommend that you actually do it yourself. All right? So start at 0, 0, plot a point at 0, 0. You would move off to the right, following the slope that is directed. All right? And this one tells me to move down here, and then kind of bends, and then bends up, and then gets even steeper to the right. And then if I go off to the left side, I'm following that curve. I've got a bend because it told me to bend. Then it keeps bending even further, bends down this way, and there we go. All right, now notice, theirs appears to drop underneath that line. Mine went a little bit above it. That's okay. It doesn't matter. You can see a little difference here compared to here. It does not matter. These are sketches. They are not perfect. All right? I put an even bigger view of the same differential equation. These figures 7 and 8 show the same differential equation with a lot more slopes drawn. All right, so the slope fields are even more impressive, and then they're here in figure 8 are a bunch of possible solutions. This red one in the middle is the same curve that we just drew. It's the same as these two. All right, only it's shown on a window that has a lot more values in it, a lot more mini slopes drawn. It looks like 1, 2, 3, 4. Every quarter value, every quarter point, they're putting a slope field or a mini slope. All right, and then they're drawing actually a couple of different members of the same family of solutions. All right, so this would be saying, for instance, that if the point 0, 1, that would be 1, 2, 3. So 0, 1 was on the curve, then you would get this curve. If the point 0, 2 was on the curve, you'd get this curve, and so on and so on. You can get different curves if you change the initial condition. All right. Finally, on the last page, I'm going to leave this here. You could pause the screen and look. I just gave one more example for those who needed a little bit more clarification. Here's a differential equation. They gave an initial condition. There's a table here of values. There's a table here of values. It doesn't matter. You can see the y values. It doesn't matter what the y value is because you're squaring it, so positive or negative is affected the same way. So that's why they've combined them all here. But so this actually counts for 2 points, -2, +1, -2, -1. You're going to get the same value. But the table is spelled out, and then the solution is actually shown, the solution curve, I should say, is shown here when it goes through the point 0, 0. All right? So that concludes, that is direction fields, slope fields, a very interesting little geometric strategy for sketching solutions to differential equations. Hope you enjoyed it. Thank you.